Hello folks, so let's look at this test. Let's see if I can correct what mistakes we've made. Help us understand what we did wrong. So, looking at this, what I printed out, what I originally wrote, was not necessarily what went on to the test. So I had to fix this. Now, what term or phrase would be used to describe a mixture that is uniform in composition, like salt in water? Salt in water. Uniform as homo. Homo. Essentially, homo means same. Hetero means different. So if it was not uniform, like oil and water, it would be hetero. But anything that is uniform, it's homogeneous. The next problem. What element is represented by the following electron configuration? 1s2, 2s2, 2p6, 3s2, 3p2. So they all cannot be represented by this. So let's look. 1s, here's our s, 1s2, 2s2. 2p6. We're here at neon. 3s2, 3p2. 3p2, that is silicon. Nitrogen freezes at negative 320 Fahrenheit. What is this temperature in Kelvin? Wicked cold, that's what it is. So the two equations we need are as follows. Fahrenheit minus 32 times 5/9 equals Celsius. And Celsius plus 273 going to be equal to Kelvin. So first thing, so negative, so 320.44, negative. So I start by subtracting 32. I get 352.4. So negative 352.44 times 5/9. Times 5 divided by 9. I get negative 195.8. So that's my degrees Celsius. Now I have to add 273 onto that. So when I add 273 onto that, you get 77. Wicked cold. Wicked cold. Black light. Our light bulbs made out of modified glass that block out all but a certain wavelength of ultraviolet light, just barely above visible. That would cause certain dyes to glow, fluoresce. How much energy is being released by 350 nanometer black light rays? Just below. So I've already identified what I'm going to get. But the equation is C equals lambda nu and E equals H nu. So the first thing is C at 2.998 times 10 to the 8th meters per second. And I'm going to divide by my wavelength. divided by my wavelength. My wavelength, 350 nanometers, needs to be converted into meters. So there are 1,000,000 nanometers, not just a million, sorry, 1,000,000,000 nanometers in 1 meter. So this is going to be 3.5 times 10 to the negative 7th. So step 1, divide my 2.998 E8. I'm going to divide by 3.5 E7 negative. When I divide that, I get my frequency to be 566 times 10 to the 14th inverse seconds. Damn it. Okay, sorry. Okay. Now, energy is going to be H 6.626 10 to the negative 34th joule seconds times frequency. So I'm going to do that. 6.626 E34 negative times my 8.566 E14 positive, and I get 5.68 times 10 to the negative 19th. But what did I tell you in class? Anything that is visible or near visible is going to come out approximately at 10 to the negative 19th or thereabouts. Had you recalled that, that would have helped. Okay, this one was one of the ones I thought should not be missed, but a lot of people missed. So the bottom number is your atomic number. Top number is my mass number. There's my charge. The atomic number is the number of protons, and that never changes. The mass number is the protons and the electrons together. So 42 plus the neutrons must equal 96. So I don't ever expect people to do mental math. So 96 minus 42 is 54. And the charge is the difference in the protons and the electrons, because the electrons are negative. So that means there must be 3 less electrons. 3 less electrons. So we must have 39. Because 42 minus 39 is 3. Same thing here. 17. So 37 minus 17 is 20. And 17 minus E is negative 1. So there's 1 more electron at 18. This one, even if you got it, the first part, you had to understand that there's P4. So how many atoms of phosphorus are in this compound? So 35 moles times Avogadro's number to the 23rd molecules of P4O10 and 1 mole of P4O10. But then we have to remember there's 4 P's in 1 P4O10. So doing that. Step 1, 35,6022 E23. That gives you answer number A, letter A. When you multiply that number by 4, you get answer, in this case, C, 8. So this is P4010. This is P. And with that in mind, okay, let's ham radio frequency. Kilohertz. So that means there is 1,000 hertz in 1 kilohertz. So there is something like 5.405 times 10 to the 6th hertz. That's my frequency. So we are using C equals lambda nu. So 2.998 times 10 to the 8th divided by my 5.405 times 10 to the 6th. That's meters per second, and this is hertz, which is the same as inverse seconds. You're going to get a number that is not too small. It's actually going to be rather big. E8 divided by 5.405 E6. I get 55.5. Radio waves are huge, but they're not this huge. Way too big, way too big. Way, way, way too small. Now this, don't forget lab. Lab is everyone here has lab, and as long as you're paying attention in lab, you should be able to do some of these. Basically, like, how do we measure something? You take the difference. If I take 42,058, which is beaker plus sample, and I subtract out the 35,078, which is beaker, whatever remains is my sample. 42,058, 35,078, and I get 6.980 grams. Now, with that in mind, density, that's my density, mass divided by my density equals volume in milliliters. So if I take my mass, 6.980 grams, divided by my density in 1.1132 grams per milliliter, my answer is going to be in milliliters. 0.1132. So I get 6.270 milliliters. I wanted all those digits. All those digits. We shouldn't have rounded. 1, 2, 3, 4. 1, 2, 3, 4, 5. We keep 4 sig figs. 4 sig figs. So hollow sphere. So looking at what you described, the pure hollow sphere, that's your S. The clover leaf, that's my D. The donut, that's also a D. The bow tie was the closest one. another lab problem, this time from the Properties of Light lab. Iron thiocyanate has a molar absorptivity of 10700 liters per centimeter mole. According to Beer's law, this would have absorbance of 0.734. What is the concentration? So A equals E times path length times C. So 0.734 divided by E, and my path length is equal to my concentration. Well, my E was 10700, and my path length is always 1.00. So literally, all you had to do, if you realize this, you'll kick yourself, divide these two numbers. You get a really small number, but 6.8. 6 times 10 to the negative fifth. So we're moving 1, 2, 3, 4, 5. What is the full electron configuration of S? So S2 minus. So here's S. So 1 S2, 2 S, 2 S2, 2 P6, 3 S2, 3 P4. This is the electron configuration of sulfur 0. Sulfur 2 minus, negative 2, we have add 2 electrons. You got to remember, when it's negative, we're adding electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. So we're going from here, boom, boom. I gave a lot of partial credit that probably shouldn't have been given on that one. Using the electron pair diagram below, how many electrons would be unpaired in the element iron? Iron right here. 26 electrons. Where did I get that 26? Right there. 26. Putting them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So how many are unpaired? 4. 4 electrons are unpaired. What is the correct electron configuration, condensed electron configuration of selenium? Selenium, remember, we always start from the noble gas. We never start from anywhere else. So zinc, boom, right out. So you want to start argon. So where do these differ? That's 4s2, 4d10, 4p4. That's 4s2, 3d10, 4p4. That's 4s2, 3d10, 2p4. This is a 3D group. So it's S, 4s, 3d, back to 4p. So this one's wrong because, this one is the right answer. This one's wrong because of the 4D. This one's wrong because of the 2P. So this is the important. Now, this one, I mean, we can factor this in as part of the curve. But which one of these would you expect to have the lowest electron affinity? And by that I mean the one that's closest to 0. Generally speaking, electron affinity is highest upper right. Highest upper right for electron affinity. Now there are exceptions. So rubidium's right here, aluminum's right here, selenium's right here, and chlorine is right there. So ideally, you would expect rubidium to be the answer, and that's what I put as the crib. Technically, if you look up values from some sources, aluminum is slightly lower. Surprisingly, it's slightly lower. But which one would you expect to have the lowest electron affinity? Rubidium. So, in the future, that mistake will not be made. Isoelectronic series. Place these isoelectronic series in order of decreasing size. Generally speaking, positive is small, negative is big. So if we're trying to decrease in size, we want to go from big to small. So which one doesn't have the negatives? Go to positives. It's this guy. This is increasing. Next problem. Read this value to the correct significant figures. So that's 20. That's 30. There's 5 numbers between each big line. So this is 25. This is 25. And so we read the bottom of this meniscus. So not only is this 24, that's the best digit there. However, we must then make an estimation. You're going to eyeball how close is this to the line. 24.0 is probably the best answer, though I accepted like plus or minus 2 or 3 to either side. If you went much further than that, you may have lost a few points. But because it's definitely not here, it's definitely not in the middle there. So, but you wanted to go 3 sig figs for that number. Finally, for this page, which of the following elements has the following ionization energies? So 787. This is almost 3 times the value. Well, it's 2 to 3 times. We'll say it's 2 times. And there we add another about 800 to get to about 323. Actually, well, adds about like 1800 to get to 323. And then fourth, then another 1100 to get to here. But from that, so let's say 2000. 2000 is a pretty big jump. However, what's the jump between here and here? The jump between here and here is about 11.7. Instead of 1100 jump, it's 1100 jump. A huge jump. So 1 loss, 2 losses, 3 losses, 4 losses. Big jump. So 4 losses means it's an element in group 4A. 1 loss, 2 loss, 3 loss, 4 loss. What element is in group 4A? silicon. Silicon. Three more questions. Which of these trends decreases going left to right? I guess technically we could say electron affinity, but the one I was looking for is atomic size. The size decreases going left to right. This does get more negative going left to right, but would say the electron affinity, the likelihood of the electron being added would increase going left to right. So atomic size is the best answer if you're not trying to be all like rules lawyer on English. So it's kind of iffy. Not the best question. I'll have to fix that in the future. Sodium. Full electron configuration. So we should end at sodium. 1s2, 2s2, 2p6, 3s1. That's all. Now this one is a challenge problem. The moon weighs 7.35 times 10 to the 22nd kilograms, or converting that, 7.35 times 10 to the 25th grams. Now, the average mole weighs 128 grams. What would weigh more, a mole worth of moles or the moon? Well, 128 grams per mole and 6022 times 10 to the 23rd moles per mole of moles. So let's do this math. 6022 E23 times 128. Surprisingly, a mole of moles weighs 7.708 times 10 to the 25th grams. Slightly heavier than the moon. A mole worth of moles would weigh more than the moon, which is surprising. Lastly, bonus. Technically, I accepted a lot of different things. All homework is technically due at 11:59 p.m. on Tuesdays. That gave you the most credit. Tuesdays or Tuesday night gave you some credit. There's some people got like kind of spicy with their like, oh yeah, it's not due till the end of the semester. Well, technically yes, but technically I also usually mark down what you've done up to that point on Tuesday. Say, what have you done once this has become due? I accept everything late, oftentimes with no penalty, but Tuesday's 11:59 is the best response. Okay, that is it. We will have to work on our math. That is one thing that has become abundantly clear. We need to work on our math a little bit more. So hopefully we can do better on this upcoming test.